We will leave the Q&A at the end of the day, if that's okay with you. If you have any questions at all that you feel like asking, and maybe you forgot by the end of the day, I would encourage you to write down on a piece of paper. It's up to you how you want to manage this. You write a piece of paper, hand it to any of our staff, or at the end of the day, you can always raise your hand and ask the question. So we'll leave the Q&A for all these topics right at the end at 3 o'clock. The closing remark period, we will have a Q&A. Okay? My closing remark cannot be half an hour, it's too long. Okay? So that period, we will leave it for the Q&A session. So without further ado, let me just hand over the time to the next speaker. That will be Vincent Price, presenting to us the next topic, choosing appropriate methodologies for mycotoxin analysis.
Good morning. It's a pleasure for me to be here in Korea. It has been since 2002 that I have not been in Korea. I came here to watch the World Cup soccer tournament. I enjoyed it very much. While I was here, I learned very little Korean. I learned 안녕하세요, 감사합니다, and 대한민국. This topic is one of chemical contamination. The next topic is mycotoxins. Mycotoxins is a topic of great concern, especially in the European Union, where they regulate mycotoxins very heavily. This is an outline of my talk. What are mycotoxins? I'll discuss some drivers for why we analyze mycotoxins, and then some analytical approaches, sample preparation techniques to choose, and also the instruments and techniques to detect mycotoxins. I will also talk about some pros and cons of the cost analysis and of the different approaches, so which technique to use based on cost. So, what are mycotoxins? Mycotoxins are toxic secondary metabolites produced by fungi under certain conditions. So you have a fungus that grows on the wheats, on the hops, on the corn, especially under conditions of high humidity and high temperature. Normally we find mycotoxins forming in countries around the equator of the Earth. In fact, we normally see them in a band of 40 degrees latitude north and 40 degrees latitude south of the equator. But in recent years, we're finding mycotoxins coming from countries that are even beyond this band of 40 degrees around the equator. And this is mainly due to global warming and the climate change. There are over 400 mycotoxins identified from 150 species of fungi, and there are various adverse effects to human and animal health. Typically, we see the mycotoxins entering into the animal feed and affecting the animals with problems of growth and illness and even death. And then this contamination can go into our food chain because we eat the animal. Here are some main groups of mycotoxins. We have the very toxic aflatoxins, B1, B2, G1, G2, M1. There are the ochratoxin, ochratoxin A, trichothecenes, the T2, HT2, and deoxynivalenol, which is also called DON, D-O-N. These T2, HT2, and DON are of high interest to the European Union, which is setting maximum residue levels for them. Also, fumonisins are very important, ergot alkaloids, and patchoulin, which sometimes we can find in apple juice. The point of this slide is to look at the different different chemical structures of these mycotoxins. They're very different, and this is what presents a challenge in the analytical laboratory to detect for these mycotoxins. Here are some examples of legislative requirements in the European Union. So the European Commission has set these regulations, the first one for setting maximum levels for certain contaminants, including mycotoxins. The second one is for setting maximum levels for the fusarium toxins. And the third one deals with methods of sampling and analysis the levels of mycotoxins in foodstuffs. So the European Union has been very busy with regulating these very toxic chemicals. There is a broad range of maximum levels. You can see one here in the PPD level for infant formula. This is aflatoxin M1 in infant formula. And at the ppm level for DON, deoxynivalenol in unprocessed cereals. So we have a broad range of maximum levels. We have many different kinds of mycotoxins, and we have many different kinds of foods. So again, this presents a big challenge in the analytical laboratory. First, it is important to have a good sampling plan. This graph, these two graphs, they represent a matrix and contamination. So the white circles are the food, the matrix, and the red circles are the contaminant, the mycotoxin. Unfortunately, infection of mycotoxins is a random event. It's not homogeneous throughout the matrix. It can happen in different places. So this presents a problem when sampling. And it's important to take a representative sample and follow a systematic sampling plan. The best way to do this is to take many samples and then mix them up and test for the mycotoxin. Now for detection. To start off with detection, there are some quick screening methods. For example, there are immunochemical-based detections. We have ELISA kits and lateral flow devices. The ELISA kits typically require a microplate reader, and the lateral flow devices, or strips, are more color-coded based. There are other techniques, biosensors, plasmon surface resonance, several techniques. These techniques are simple, easy to use, and they are quite cheap. We can use more sophisticated techniques with analytical instrumentation. For example, we can use near IR or near infrared techniques. We can use Fourier transform infrared techniques, also known as FTIR. These techniques are molecular spectroscopy techniques. They're also called vibrational techniques. The reason they're called vibrational techniques is because you shine a light through the sample, and that light will contain many different wavelengths of light. And this light will make the compound, the mycotoxin you're looking for, it will make it vibrate and twist and bend and absorb the energy of that light at a particular wavelength. And it absorbs different energies at different wavelengths. So you get a spectrum, a characteristic spectrum of your sample. Here on this axis is the wavelength number of the light, and on this axis, the y-axis, is the absorbance of that light. So again, you can get a spectrum of a particular mycotoxin. Down on the bottom is our infrared spectrometer, thermoscientific infrared spectrometer. And on the top is our thermoscientific near IR spectrometer. Here is an example of some results with the mycotoxin DON in cereals. You can see the wavelength number, and the bottom spectrum is a Dawn standard. So we can see that Dawn absorbs at about 7,095 wave numbers here, and also in other areas like 5251. We can spike a sample of cereal at 10 ppm, and we can see that it absorbs right where Dawn absorbs, which is to be expected. We can also test a naturally contaminated sample at 13 ppm, and again, we see the absorbance right where we expect to see it for Dawn. So near IR is a nice technique to use to identify a contaminant like Dawn in the sample. We can also use chemometrics techniques. Chemometric software is a good tool to plot out the differences of many different samples. So we can classify samples in different regions based on characteristics of the sample. Here we have some dots that are the blank calibration samples in red. The greens are blank validation samples. We can have contaminated calibration samples, contaminated validation samples, and they all fit in different areas of the graph. So we can use the results of near IR on chemometric software to characterize our sample. Now I want to move to more sophisticated techniques with analytical instrumentation. I want to talk about chromatography and mass spectrometry. So you have very simple techniques like thin layer chromatography. This is not being used so much in the food labs. What is being used a lot are liquid chromatography and gas chromatography. The liquid chromatograph can have a standard detector, or it can be coupled to a mass spectrometer. Same for a gas chromatograph. It may have a standard detector, like a flame ionization detector, electron capture detector, or a more sophisticated mass spectrometer. Depending on which detection device will be used, you would have to do a different sample preparation technique. For example, we can start with an extraction with solvents such as acetonitrile in water or methanol in water. We may need a cleanup step like a C18 column or using an immunoaffinity column. As Dr. John Gilbert was explaining, immunoaffinity columns can be very selective, very specific for a particular mycotoxin. So you would add the sample to the immunoaffinity column, and then you would, the immunoaffinity column has antibodies that bind to the mycotoxin. You can wash out the column afterwards of everything else that's in the matrix and just be left with the mycotoxin, which you can take out afterwards. Then you may need a derivatization step for aflatoxins or fumonisin or trichothecenes like Dawn. And then you have the detection step. You have the separation in a liquid chromatograph or a gas chromatograph, and then detection with a standard detector or with a mass spectrometer. Here is an example of an aflatoxins method. This is a SEN method. SEN is the European Committee for Normalization, and it is a repository of methods. This is an aflatoxins method for aflatoxins B1, B2, G1, G2 in hazelnut paste. This is the workflow of the method, and you can see it starts out with a homogenization of these hazelnuts, then an extraction with water and methanol, a filtration step, and then onto an immunoaffinity column that I just described before. After that, a short evaporation step, and then onto a liquid chromatograph with a fluorescence detector. This step, the immunoaffinity column cleanup step, is very important in order for the fluorescence detector to see the aflatoxin. If you do not complete this step of cleanup, then the fluorescence detector will not be able to single out the aflatoxin. There will be too many matrix effects. Sometimes laboratories do not have liquid chromatographs. Maybe the laboratory has a gas chromatograph. You can still analyze for mycotoxins with GC. Typically for DON, T2, nivalenol, etc. You can use an immunoaffinity or an SPE cleanup. SPE is solid phase extraction. Perhaps you will do a derivatization and then an analysis by the GC with an FID, ECD, or a mass spectrometer. And you can get pretty good limits of detection in different matrices. So you can use the GC, but you have to realize that a derivatization step will be needed and some cleanup will be required. When trying to determine an analytical method, what kind of method to use, you typically have to consider three things: cost, speed, and performance. Usually, you can optimize two of these three things, but you can really never optimize all three. For example, you may have a method that is very fast and very cheap, but the performance, like the selectivity or the limits of detection, may not be so good. On the other hand, you may have a technique that is very fast or that has very good selectivity, very good limits of detection, very good repeatability, but it costs a lot. So these are the natural trade-offs that we have to make as analytical chemists in a laboratory. Here is another way to understand this situation. This shows the relationship between cleanup efficiency and the detection selectivity of different techniques. For example, you may want to use a very simple and inexpensive technique like HPLC with a simple UV detector. But in order to do that, you will have to use a more efficient cleanup like an immunoaffinity column. Immunoaffinity columns are very efficient, as I was describing before. One drawback is that they are expensive. They typically cost about 20 to 25 euros or dollars per column, and you can only use them once. But they are very, very efficient in the cleanup process. And certainly, an HPLC with a UV detector is not very expensive. On the other hand, you can settle for a very simple extraction technique, but you'll need a more sophisticated instrument like MSMS triple quadrupole mass spectrometer, or even high-resolution mass spectrometry like our thermoscientific Orbitrap. So the more sophisticated the instrument, the less efficient cleanup that is necessary. I'd like to explain why that is. But first, here's a quick method of mycotoxins in food and feed. A very simple homogenization step, like I showed before. Very simple extraction with acetonitrile and water. simple filtration step, and then a quick dilution and injection onto the LC-MS. This is a very quick and easy sample preparation step. It does not require the cleanup of the, or by the immunoaffinity column. And that is because in this case we are using a much more sophisticated instrument, which is LC-MS. I'll go into the details of why you can skip the efficient sample cleanup when you use LC-MS. LC-MS is triple quadrupole mass spectrometry. There are 3 quadrupoles. A quadrupole is a set of 4 poles like this laser pointer. And the poles have an electromagnetic field on them. They are designed to either to fragment ions or to propagate ions. So the first quadrupole here is called Q1. The second quadrupole is Q2. The third quadrupole is Q3. Here we have a selectivity of 0.7 Daltons. We are looking for an ion, and we're going to tell the quadrupole, the first quadrupole, to select for us the mass-to-charge ratio of 408. In this example, there are 2 ions that are close to 408. We have 408.2 and 408.4. That first quadrupole will select out 408 and eliminate all the other ions. These are called precursor ions that we're looking for. So the precursor ions go through the first quadrupole and they enter the second quadrupole. This second quadrupole is also called a collision cell. It's filled with charged gas, and it will fragment the precursor ions into smaller product ions, as you see here. Those product ions will enter into the third quadrupole, which will filter out only the product ions that we're interested in, like you see in the diagram. So this technique is called selective reaction monitoring, SRM. It's a very common technique with triple quadrupole mass spectrometry. Again, the resolution that we're using in this example is 0.7 Daltons on both quadrupoles. We can increase the selectivity from 0.7 Daltons to 0.4 Daltons. In fact, even more than that, perhaps go down to 0.1 Daltons. When we increase the selectivity, then we can really be more selective with the precursor ions that we're filtering out. So, instead of having these 2 precursor ions, we can only have 1 come through, which is what we want. This is being more selective. Again, the precursor ion enters Q2 and gets fragmented in the collision cell and goes through Q3, and we see really only the product ion that we're looking for. By tightening up this selectivity to 0.4 Daltons, we are using not SRM, but HSRM. H stands for highly selective reaction monitoring. And Thermo Scientific is the only company that can offer HSRM. The reason for that is because we designed our quadrupoles with a hyperbolic design, a hyperbolic shape. So if you look at a quadrupole from most manufacturers, it looks like this laser pointer, round. But ours are hyperbolic, and that creates for a more efficient filtering of the ions. Here's an example of HSRM with mycotoxins, in this case diacetoxyscripinol, in wheat. If we use normal selective reaction monitoring, or SRM, we see the peak here for the mycotoxin, but we also see a lot of other peaks around it, and that's part of the matrix. These are other ions that are getting through that first quadrupole. If we use HSRM, we can really single out a very nice peak and be more confident in our result that this is the diazoxyribonucleic. When we don't have the other interferences here, we have a nicer peak and we can do better quantitation as well. Now I want to move to an even more sophisticated technology, which is Orbitrap technology. Orbitrap technology was invented by Thermo about 5 years ago. It was originally designed for big pharmaceutical companies who were doing proteomics analysis. So the original purpose was to identify as many proteins as possible in a day. The food laboratories had a difficult time using Orbitrap technology because it was a very big machine and it was very expensive. But in the last 2 years, we have reduced the size of Orbitrap technology, and we have also reduced the price. So now it's more affordable for food testing laboratories. But it's still Orbitrap technology. This product is called the Exactive. So you will hear that name throughout the day today, Exactive. The technology that's used inside is called Orbitrap technology. With Orbitrap technology, the separation happens in the chromatograph, then the compounds are fragmented, and those ions enter into an electromagnetic cell. This is a representation of the electromagnetic cell. There is a spindle that goes through the middle of the cell here, and when the ions go in there, in this environment with an electromagnetic field, they orbit around the spindle and they start to oscillate. The smaller ions oscillate very quickly. The larger ions oscillate very slowly. We can measure the frequency of this oscillation with very high precision. This gives us the ability to really detect the masses with high accuracy. It also gives us the ability to have very high resolution on this mass spectrometer. Here's an example. These are results from an institute in the Czech Republic. The Czech Republic, the people in the Czech Republic are very proud of their beer, and they drink a lot of beer. They produce a lot of beer. So this was done by the Institute of Chemical Technology, or ICT, in Prague, and they worked with the local beer manufacturer to look for mycotoxins at different stages of the beer manufacturing process. And you can see the very nice resolution here at 100 ppm, but you also get very nice resolution at 20 ppm and at 2 ppm of a T2 toxin in a beer extract. They also did work with comparing results at different resolutions. Here is the same study, T2 toxin, in beer. And this is at resolution of 25,000. You can see there's a peak in here of the T2 toxin, but you see a lot of interferences at 25,000 resolution. 25,000 resolution is on the high side of what a time-of-flight mass spectrometer or a TOF mass spectrometer can achieve. I think the most most that I've seen for a TOF is about 30, maybe 35,000 resolution. So this is the kind of result that would be expected with the time of flight mass spec. But with Orbitrap technology, we can increase the resolution to 50,000 or even 100,000 and get a very, very nice peak of our mycotoxin. You can also be quantitative when you use Orbitrap technology. Here are some limits of quantitation of the mycotoxins that were found in the beer study. The limits of quantitation here, but it's also very repeatable. You can see the relative standard deviation here, all of them under 20%, which you may remember from John Gilbert's talk, is very important for European Union regulations. Here are some more examples. Again, the same analysis, DON, in beer at different concentrations. We have 5 ppb, 10 ppb, and 100 ppb. On the bottom are 2 examples of 5 ppb, in the middle 10 ppb, and on top 100 ppb. The difference on the left side and the right side is the resolution. On the left side we have 25,000 25,000 resolution, and on the right side 100,000 resolution. And you can see the difference in the peak shape. Okay, so at 100 ppb, maybe there's not a big advantage, but when you start to get to the lower levels, like 10 ppb, and look at 5 ppb, it's very difficult at 5 ppb to really see this peak at 25,000 resolution. But if you increase the resolution to 100,000, you can really see a nice DON peak there. So really, with the Exactive or with Orbitrap technology, it's a matter of finding your mycotoxin or not finding it. It's a matter of seeing it or missing it. But there's even more advantages to Orbitrap technology and this high-resolution technique. If you use high-resolution mass spec, you can also go and do post-acquisition data mining. So in this case, they found the DON in the beer, but they also, after the analysis, they went back to the data and they found other peaks that they did not see in the beginning. And these they found were the DON glucosides. So these DON glucosides can also contribute to the formation of DON as the brewing process continues. It's very important information. So again, the message is, if you really want to see everything and do unknown analysis of unknowns, which is also called non-targeted screening, then you want to use as high resolution as possible, which is only achievable with the Orbitrap technology. So I've spoken about quite a number of techniques, from the immunoassays, infrared, chromatography and mass spectrometry, all the way up to accurate mass and high-resolution mass spectrometry. So the question is, which one is right for your laboratory? Well, you have to decide. For a target screen, you can use all of these. But if you want to do quantitation, then you don't want to use immunoassays or infrared because they're not quantitative techniques. If you want to analyze unknowns and do non-targeted screening, then your best bet is to use Orbitrap technology, very high-resolution mass spectrometry. If you want to spend no time on sample preparation, you have some choices here, like the immunoassays and infrared. You can also use the Orbitrap technologies because that does not require much sample preparation. If you want to analyze many, many analytes in one analysis, then you would use a higher-end mass spectrometry technique, not some of the cheaper ones. If you want something that's fast, well, there are a number of them that are fast. But typically chromatography and mass spec are not the fastest techniques. And you also have to realize that if you want a cheap solution, you can go for the immunoassays or infrared, but as you get to the more sophisticated chromatography and mass spec techniques, they will cost more. So these are things to consider when you're deciding which technique to use. So in summary, the mycotoxins are of concern throughout the world, but the food labs can select an appropriate analytical approach depending on what you want to do. And I'd like to inform everyone that Thermo Fisher Scientific offers all of these techniques, the broadest range of techniques to analyze your mycotoxins depending on what your laboratory needs are. With that, I will say 감사합니다.
Vincent, for that nice informative session on mycotoxin. Right. This is a food safety seminar. I hope there will be a lot of good food today. Now is a break. It's a coffee break. And we will have 15 minutes coffee break. So we should come back into the room by